So equilibrium problems, starting off with an old fave, Le Chatelier's principle. Decomposition of dinitrogen 4 oxide, that's N2O4, into nitrogen 4 oxide, NO2, is a reversible reaction that establishes dynamic equilibrium. So pale yellow in equilibrium with dark brown. State the meaning of the term dynamic equilibrium. Two opposing processes happening at the same rate. So in other words, in this particular case, N2O4 will be turning into 2NO2 at the same rate that two NO2s will get together to make N2O4. Conditions applied to an equilibrium mixture of these. For each of the following, state what was seen, explain any change that occurred. So if we increase the temperature, well, the rule is that any reaction is going to go in the endothermic direction. Okay, this particular reaction, we're told that delta H is plus 57 for as written. So in other words, going to the right is plus 57. So in this particular reaction here, the endothermic direction is to the right. So therefore, what's going to happen when you increase the temperature, the reaction is going to go in this direction. So we're going to make more of the dark brown. And about if we increase the pressure, well, any reaction is going to go to the side with fewer gas molecules. We look up here, we have one gas molecule on the left, two gas molecules on the right. So for this particular reaction, this is going to go to the left. As the reaction goes to the left, the dark brown will turn into pale yellow. And finally, a catalyst was added. Well, all a catalyst will do is it will get you to equilibrium faster. Seeing as how we've already got an equilibrium mixture, it will have no effect. It doesn't change where the equilibrium is. It just, if you're not at equilibrium, a catalyst will get you to equilibrium more quickly. Reaction to make methanol is in dynamic equilibrium. There we have CO gas plus 2H2 gas, reversibly going to CH3OH gas. And they tell us delta H minus 90 kilojoules per mole. So in other words, going to the right is the exothermic direction. So use the equation above to explain the conditions, temperature and pressure that will give the greatest yield of methanol. Well, first of all, greatest yield of methanol means we want the reaction to go to the right. We want lots of this stuff. So temperature. Well, the direction that our equilibrium will move with the temperature depends on whether the reaction is exo or endothermic. Okay, we're told that this reaction is exothermic. Okay, so lowering the temperature for any reaction pushes the reaction in the exothermic direction. That's what we want here. We want it in the exothermic direction. So therefore, we want to operate at low temperatures. Pressure. Well, the effect of pressure depends on the number of gas molecules. Okay, we got three gases on the left, we got one gas on the right. We want to send it to the side with one gas molecule. Okay, and increasing any pressure for any reaction sends any reaction to the side with fewer gas molecules. Here again, three gas on the left, one gas on the right. So if we increase the pressure, we will push the reaction towards the one gas side, which is the side we want to go to. So low temperature, because we want it going in the exothermic direction. High pressure, because we want it going to the side with fewer gas molecules. Saturated solution of strontium chloride, you don't often see strontium at A-level, can be represented in equilibrium mixture between the solid, there are SrCl2 solid, and the solution. Notice in the solution, because it's an ionic compound, it has dissociated to give you Sr2+ and 2Cl- aqueous. So now we add some hydrochloric acid and a clear solution of strontium chloride becomes cloudy. Use Le Chatelier's principle to explain the appearance of this cloudiness. Well, let's see. If we add HCl, we're effectively adding Cl- and there's Cl- on the right. So we're adding a righty or a product. And for any reaction, when you add a righty, it will drive the equilibrium to the left. So as we drive this equilibrium to the left, we're going to make more of the SrCl2, which is, of course, a solid. Okay, so therefore, as we add the HCl, driving the reaction to this direction, we start making a solid. And when you make a solid in a solution, it goes cloudy. So the cloudiness is the precipitate of SrCl2, and the SrCl2 is precipitating because by adding chloride you're forcing the reaction towards the solid strontium chloride. So moving to some metal chemistry, the commonest complex ion that copper forms in solution is the hexaaquo copper 2 ion CuH2O6 times 2 plus, that one there, and that's a pretty blue color. If you add concentrated hydrochloric acid to this solution, however, a new complex forms. So there's the adding Cl- that come from the HCl. And here's our new complex forms that see yellow-green. Okay, and so we establish this equilibrium between the blue and the yellow-green as we're adding in that HCl. And it tells us the forward reaction is endothermic. So state and explain what you'd observe on adding water to the equilibrium mixture. Well, water is over here in the reaction. It is a product, a righty. So what we're effectively doing by adding water is we're adding a product. Any reaction, if you add a product, gets driven to the left. To the left means we're making more of the CuH2O6 times 2 plus, so therefore the reaction is going to go bluer because we're driving the reaction towards the blue complex. State and explain what you'd observe on heating the equilibrium mixture. Well, for any reaction, when you raise the temperature, the reaction goes in the endothermic direction. Here we're told the forward reaction is endothermic, so therefore raising the temperature pushes the reaction towards the right. As we push it towards the right, we're going to make more of this CuCl4 2-, which is of course yellow-green. So heating it up means the reaction is going to be turning yellowy green from the blue. So a pretty question here, I thought. Nitric acid produced by the Ostwald process, jolly good, you need to know it, just not really for this question. First stage involves the oxidation of ammonia, so that's ammonia being oxidized over a platinum rhodium catalyst to make nitric oxide and water. The graph below shows how the yield of nitric oxide depends on the temperature and pressure. So in other words, we're looking at the yield of this nitric oxide. Now as we go here, yield is going up, so therefore the lower down, the less the yield, and pressure is going across here. So the further you go to the right, the higher the pressure. And then we see this is what we get at 600, this is what we get at 800, and this is what we get at 1000 degrees Celsius. So let's see what we've got here. Okay, well, the first thing is that as the pressure goes up, the yield goes down. Doesn't matter what the temperature is, the yield is going to go down as you increase the pressure. But now we look at the three lines, and what we see is that as we go 600 to 800 to 1000, the temperature is going up. But as the temperature goes up, the yield goes down. So therefore, right, as we increase the temperature, the yield goes down. As we increase the pressure, the yield goes down. So now moving to part 2 for the same question. Use the graphs to explain whether the reaction is endothermic or exothermic and whether there are more moles of gaseous reactants than products, or obviously less moles of gaseous products than reactants. Well, first thing is, as we raise the temperature, the yield goes down. If the yield of nitric oxide is going down, that means the reaction is going to the left. Okay. Now for any reaction, when you raise the temperature, the reaction is going to go in the endothermic direction. So putting that together here, this particular reaction, raise the temperature, it goes to the left. Knowing that raising the temperature pushes any reaction in the endothermic direction means that going to the left here is endothermic, so going to the right is exothermic. So when we write the reaction as this, it's going to have a negative delta H. Now let's think about the pressure. Okay, as we increase the pressure, the yield goes down. As we already said, if the yield of this goes down, that means the reaction is going to the left. Okay, now for any reaction, increasing the pressure pushes any reaction to the side with fewer gas molecules. So if we're going to the left here, that must mean that the left has fewer gas molecules or the right has more gas molecules. Okay, so kind of a reverse application of Le Chatelier's principle. Rather than predicting what will happen, we see what will happen and then take it back to interpreting, first of all, that because the temperature raising decreases the yield, that means that going to the right must be the exothermic direction. And because increase in the pressure decreases the yield, that must mean that the right has more gas molecules on it. Finally, last part of this. So very long intro to the question. That for our particular question of interest, we don't really care. During the 2016 Olympic Games, diving pool had to be closed after the water turned green. As we're not divers, we're chemists, we don't care. Report in the media incorrectly suggested there was too much chlorine in the pool. Well, what a shock. Journalists don't know their science. Again, don't care. When chlorine gas dissolves in cold water, pale green solution is formed. Here we do care. There's chlorine gas dissolved in water, making a pale green solution and forming this equilibrium. So use Le Chatelier's principle to explain why the pale green color disappears if sodium hydroxide solution is added. So anytime we add sodium hydroxide to something, we can be sure that it's going to neutralize any H plus that we've got there. So by adding NaOH, effectively adding the OH minus, we are removing a product, removing something that's on the right. And for any reaction, when you remove a product, remove something that's on the right, the reaction will go to the right. So therefore, when we add the OH minus, the reaction is going to go to the right. It will make more of these colorless products. And in doing so, of course, it will use up the reactants, use up the pale green. So thus, as you add the hydroxide, you're turning the pale green into the colorless. Green color used up because the reaction is going to the right. And the reason it's going to the right is the hydroxide is removing the H plus. Nitrogen react with hydrogen for ammonia. Very, very important reaction, very important process, the Born-Haber process, making literally millions of tons of ammonia every year. When the temperature is increased, the equilibrium yield decreases. Student says the reaction is endothermic. Is he correct? Well, let's see. Okay. When you raise temperature, you push any reaction in the endothermic direction. Okay. Now, because here the equilibrium yield of NH3 decreases, that means the reaction is going to the left. So raise the temperature, reaction goes to the left. Raise the temperature, reaction goes to the endothermic direction. Thus, both of these are saying the endothermic direction is to the left, which means the exothermic is to the right. In other words, the student is wrong. So part of a question that we'll do the rest of a bit later on in this whole thing, because obviously we've got some numbers here. Right, but a flask contained initial mixture of this and this, kept 25 till this following equilibrium had been established. State, given a reason, what happens to the value of the equilibrium constant if temperature is increased? Well, of course, as we know by now, raising the temperature pushes any reaction in the endothermic direction. Going to the right here is exothermic. So therefore, raising the temperature would push this reaction to the left, because if it's exothermic to the right, it's endothermic to the left. If the reaction goes to the left, that means the number of reactants goes up, the products goes down. In other words, K gets smaller. Phosphorus forms two chlorides, dynamic equilibrium between them, represented by this equation. As the temperature is increased, the value of Kp increases. What information does this provide about the enthalpy change of the reaction? So, as we know, raising the temperature pushes any reaction in the endothermic direction. We also know that right here, because Kp is increasing, the equilibrium goes to the right. So putting those together tells us that the endothermic direction is to the right. Okay, increase the temperature, reaction goes endothermic. increase K, reaction goes to the right, thus endothermic is to the right. Delta H is a positive number. Chromium present anions, blah, 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 can be interconverted. This is actually part of a very complex question we'll do some more of in a later movie associated with this worksheet. But right now, the value of the equilibrium constant increases when the mixture is warmed. What information does this provide? Well, again, increase the temperature, any reaction goes endothermic direction, just like the last question, the equilibrium constant increases. Well, if the equilibrium constant increases, that means you've got more right than left, so therefore the reaction is going to the right. Put them together, endothermic means it's to the right, delta H is positive. Putting those two right next to each other, just to let you know the examiners like that particular idea. Student given a pink colored solution containing these cobalt hexaquo or hexaquo cobalt 2 ions, that's there, pink. Add in HCl, which is the same as adding in Cl minus, it turns blue as you make the COCl4 2- ions forms. This is exactly analogous to the copper question that we looked at earlier, where we turned blue into greeny yellow. Okay, very, very pretty reaction here. It will be a demonstration of it will be loaded up to our A-level website at some point because it's just really pretty and fun. Anyway, aqueous silver nitrate was added to the solution containing COCl4 2-. So we got blue solution. Of course, that blue is in equilibrium with this, but it's more blue than there is pink, so it looks blue. Now, anytime you see silver nitrate, you need to think halides because, of course, silver plus reacts with halides, in this case it's chloride that's of interest, to make the insoluble silver halide. So the silver ions will pick up any chloride that's in solution, precipitate it out as AgCl. Well, is there any chloride in this solution? Absolutely, right there. So therefore adding the silver ions, don't care about the nitrate, adding the silver ions removes the Cl minus. So we're removing a reactant, we're removing a lefty as a precipitate. Any reaction goes to the left when you're removing a lefty, thus we're going to go here and the reaction will turn pink. It actually looks kind of like a strawberry milkshake because you've got this pink solution, but you've got this white solid precipitate of the silver chloride dissolved in it. So it's cloudy and pink. So like I say, like a strawberry pink milkshake. Nitrogen dioxide is used in the production of nitric acid, which is, of course, the Ostwald process, as we learned earlier, produced in 2 stages. There's the ammonia with the oxygen, making nitric oxide and water. We looked at that previously. And stage 2, 2NO plus O2 goes to 2NO2. Why is the use of a catalyst essential in industrial processes involving exothermic equilibria, such as these? In particular here, stage 1. Well, let's see. You want reactions to go quickly, and ordinarily you can make them go more quickly by heating them up. Trouble is, of course, this is an exothermic reaction, so when we heat it up, it drives the reaction to the left. So therefore, we don't want to have it too hot, but we do want it to go quickly, and so we can use a catalyst to speed it up at the lower temperatures. Again, same question, different part. Student attempted to perform stage 2 using a temperature of 450 Kelvin, pressure of 5 atmospheres, only got a small yield. How could the student improve the yield? So we don't care about speed here, we care about yield. We want to get the reaction, the equilibrium, going to the right. Well, let's think first of all about temperature. Okay, the reaction is exothermic going to the right, so therefore how do you make a reaction go in an exothermic direction? You lower the temperature. So remove 450 Kelvin, do it at a lower temperature. Now let's think about the pressure. Okay, the reaction has fewer gas molecules, 2 on the right compared to the 3 that are on the left. Okay, so we want to drive the reaction towards the fewer gas molecules. An increase in pressure pushes any reaction to the side with fewer gas molecules. So a student wants to lower the temperature and increase the pressure. Now, of course, there are other ways in which you can adjust what's going on other than temperature and pressure. Any reaction can be driven to the right, which is what we want, by either removing the product, so if there's a way that you can remove the NO2 as it forms, you're removing a righty, reaction will go to the right. Or alternatively, you can continually add reactants, because as you add reactants, you increase the concentration on the left. As you increase the concentration on the left, it will again drive the reaction to the right. So the student could do quite a few things: lower the temperature, which of course will slow the reaction down, but he or she, I guess, will get a better yield. Can increase the pressure from 5 atmospheres, taking it up a bit. Now, of course, remember there is a relationship between temperature and pressure. Increase the temperature, increase the pressure, increase the pressure, increase the temperature. So there'll have to be a compromise sorted out there. But then you can also drive any reaction to the right by either removing the products or adding in lots and lots of reactants.